Hello everyone, my name is Chami9 and my CWID is 2059561. So for this extra credit project, I went for number 3, which is bicycle design, and this is to optimize the performance of a bike. And the day I completed this is on June 20th, 2025. Okay, let's get started. Introduction. Bicycle gears are crucial for the optimal performance of a bicycle and the cyclist. And in this project, I'll explore the role of bicycle gears and pedals in the context of different speeds, road inclines, and the cyclist's power output. And then I'll analyze the forces acting on a bicycle and create a pedal to optimize the rider's efficiency. Okay, so now I'm getting into the concepts first, and then I'll get into the calculations. So for gears, obviously, every bicycle has gears, and basically they allow you to adjust how much force you want to use. Uh, for example, in here on gears and road incline, lower gears help the cyclist push against gravity, which means when you're going uphill, you usually set it to lower gear, and when you're going downhill or a flat surface, when you want to go faster, you usually use higher gears to maximize the the efficiency. And in gears and speed, higher gears are typically used for faster speeds. Just like I said, higher gears are used for faster speeds on a flat or when you're going downhill. And gears and rider power output. Yeah, so depending on the surface that the rider is riding on and the rider's energy potential, you can adjust the gear. Next. So first we're talking about air resistance on a bicycle. So air resistance is a significant factor when it comes to the forces acting on a bicycle, especially at higher speeds. Like the faster you go, the more air resistance there is. So the formula I went for is uh, drag force is equal to 1 over 2 times density of air times velocity square times drag coefficient times the frontal area of the bicycle and rider. And here we assume the density of air to be 1.225 kilogram per meter cube and the drag coefficient 0.8. And for A, we assume it to be 0.5 meter square. And here we can assume the speeds to be 12 meter per second, 15 meter per second, and 18 meter per second. And over here, when we calculate, we get this. I basically just plug in the values into its corresponding position. And at velocity equals 12 meter per second, we get 39.69 Newton. At velocity equals 15 meter per second, we get 62.02 newtons. At velocity equals 18 meter per second, we get 89.30 newtons. Yeah, so these are example calculations. And the next force is slopes. So depending on whether you're going uphill or downhill, gravity does act on your bicycle, obviously. And the traditional formula is f of g is equal to mg sine theta, sine theta. M is the mass, g is the acceleration due to gravity, and theta is the angle of the slope. Here I assume the human to be 67 kilograms and the bike to be 10 kilograms. So in total, it's 77 kilograms. And I assume slopes to be 12 degrees, 15 degrees, and 18 degrees. And here, when we calculate it, for 12 degrees, we get 157.1 newtons. At 15 degrees, we get 195.5 newtons, and at 18 degrees, we get 233.4 newtons. So once again, these are example calculations on how slopes affect the affects the bicycle. And over here, this is the third force, which is the rider's power output. And obviously, this is the one who is pedaling the bike, how much power output they produce. And over here, we assume like someone who rides for leisure or for recreation, they produce around 75 to 150 watts. And a beginner rider, they usually produce around 150 to 300 watts. And for a professional rider or someone who is riding at a faster rate than a normal person would, they will produce 300 to 500 watts. And this is a power formula. P is equal to F total times velocity. So P is power in watts, F total is the total resistive forces, and V is the velocity. Next, over here, I have designed a pedal for torque. So the pedal system is designed to allow the rider to create the necessary torque to propel the bicycle. Torque is the rotational equivalent of force. So formula here we got T equals F times R times sine theta. T is torque, F is force, R is the length of the crank arm, and theta is the angle between the force breaker and the crank arm. And here we assume the rider's weight to be 67 kilograms, just like before. And we assume 70% of rider's weight can be applied effectively as a downward force during the power stroke. And here, by applying the formula, which is F equals 0.70, which is 70%, times 67 kilograms, which is rider's weight, times acceleration due to gravity. And we get 460 newtons. And we assume the crank length arm to be 0.18. Sorry, I forgot to change this. Right, it was a typo. I I meant it to be 0.18, but accidentally typed 0.17. Anyways, so we assume the crank length arm, the length of the crank arm to be 0.18 meters, and the angle to be 90 degrees. So sine 90 degrees is equal to 1. Over here, we're plugging in the formula, which is this one, plugging in the values, 460 newtons that we got from here, times 0.18 times 1, we get 82.8 meters. And now, here are the results. And this is for air resistance, as you can see, when V is equal to 12 meter per second, we get this. 15 meter per second, we get this. And 18 meter per second, we get this. Conventional forces, same thing, just like I told in the previous slides. This is just the a summary of my findings, my calculations. Next, discussion. So based on calculations, drag force becomes the most powerful resistive force at higher velocities. Because as speed increases by double, drag force increases 4 times. For gearing, lower gears are important for climbing because they allow the cyclist to maintain appropriate rhythm and power output, which prevents rider from getting easily tired. And going back to the slide, I forgot to mention, um, this is the optimal performance because of 3 reasons. First, I converted the rider's weight and effort into a downward force on the pedal. Second, I maximized leverage by using the crank arm length to create torque. And third, I applied the force at the most advantageous angle to produce maximum torque. Yep. Moving on. So pedal design, my example shows that with the right pedal and crank arm setup, a rider can actually use their own body weight to generate a lot of torque, or turning force. That's very helpful when you're starting from a stop or trying to go uphill. So what's the point? A good bike design finds the right balance. It cuts down things that slows you down so that the rider can push forward. And when we understand how a bike works, then we can select the right parts, the right gears, the right crank lengths to whether for our different riding purposes. And as technology improves, we are making better, smarter bikes to make riding smoother than ever. And this is it. This is a reference. Thank you.